Hi, all. Welcome back to another round of astronomy, and yeah, let's get at it. Question for you. So, I have four situations. Pretend that you're a person and you give a ball a shove. Go ahead, take a minute. What will happen in these four cases? Good, 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 good. Now, I use this as an analogy, but let's go ahead and walk through. So, this first case, you can imagine the ball as it rolls up and up the hill, it's slowing down, and as it slows down, it can move further and further up the hill. But eventually, it stops. And right here, after this, it starts rolling back down the hill. What I want to say is that it starts up and it will fall back, or if you will, collapse back down to the ground. Well, how about this next case? Well, so we push the ball up, and this next case, I mean for it to be kind of that boundary case, right? The ball starts rolling up, it rolls, it rolls, it rolls, it rolls, slowing down, slowing down, slowing down. And what I mean for this one is that it just reaches the top. Dink. Just reaches that plateau. But the moment that it reaches that plateau, it should have zero kinetic energy. It should just get right up to the top and stop. Of course, this bottom one, you can see that when it reaches the top of the hill, slows down, slows down, slows down, slows down. And so once it gets to the top of the hill, it's still moving. And so it coasts along on its merry little way. Of course, the fourth one is really exciting, right? If you push the ball and it starts going down this hill, it will just keep speeding up, speeding up, speeding up, speeding up. It, for lack of a better word, I'll say it accelerates. Or it's accelerating. Okay. Now, of course, we're not worried about a ball. We're worried about what happens to the universe. So, now we don't know the mechanism that started this. But the analogy would be, pretend that the ball is the universe, the physical universe, and we're going to pretend that the person, the thing that causes the universe to start expanding, okay, we're going to say that that's the Big Bang. And so we have four different possibilities for the fate of our universe. Let me walk you through it. The first one is what we refer to as the collapsing universe. This would be the first situation in the previous example. The Big Bang pushes the universe, which starts expanding outwards. It's like the ball rolling up the hill. As it expands outwards, it is slowing down, slowing down, slowing down, slowing down. And eventually, it stops. Well, after that moment of stopping, now it's going to speed back up, speed back up, speed back up. And sometime in the distant future, it will again return back to the ground. Sometimes, and you've probably heard this in popular culture, possibly, okay, it's called the Big Crunch. Perhaps the universe will eventually recollapse and there will be a big crunch corresponding to the Big Bang, right? The kind of the opposite. Okay? Now, that's just one situation. The next one is sometimes referred to as the critical situation. This would be the Big Bang causes the universe to expand, and it provides just enough energy, for lack of a better term, it provides just enough energy so that the universe will keep expanding, but slow down and just reach the top of the hill. In other words, way, way, way in the distant future, the universe will, infinitely far into the future, the universe will stop expanding. But since it's infinitely far into the future, we'll never actually reach that point. It'll keep expanding, but it'll be very, very slow and just about zero at the very end. The technical term for this is asymptotic behavior. So that's called the critical. It's that boundary line where the ball just reaches the top, but once it reaches the top, it stops. Of course, the third situation is that it continues, it gets to the top of the hill, and it just keeps rolling and goes at a constant rate. That's what we call a coasting universe, right? The expansion is constant and just keeps going at this constant rate forever. Of course, the last one, which is really weird, is the one where the ball rolls down the hill. In other words, not only is it expanding, but not expanding at a constant rate, but an ever increasing rate, what we would call an accelerating universe. And yes, in 2011, the Nobel Prize was given for the discovery of the accelerated universe. Okay, so how do we get that idea? We have two different ways to measure really far distances in the universe. And at one point when I was presenting these, I think I made a comment about note how they are completely different in the observables needing to be recorded. Okay. The reason I wanted to highlight that is because since they depend on completely different observables, we can say that these two distance measurements are complementary. In other words, I should be able to take the redshift of a type 1 supernova. I can use the fact that it's a type 1 supernova to get a distance calculation. I should be able to use the redshift to get a distance calculation. And theoretically speaking, those two should be in agreement. Let's go ahead and get some practice. So here we go. A type 1a supernova, 1992 BI, has an absolute magnitude of negative 19.6 and an apparent magnitude of 22.4. I did not make up these numbers. These came directly from Perlmutter's paper that won him the Nobel Prize in 2011. Okay? This is the very first supernova quoted in his paper, so don't think I made this one up. Okay? Go ahead, take a minute, figure out, according to the data, how far away should this supernova be? Got it? Good. Okay, let's walk through. I've given you the equation that relates the apparent absolute magnitudes to the distance. Now we plug in our values, keeping in mind that the absolute magnitude is represented by big M, and the apparent magnitude is represented by little m. And please don't forget, you have a double negative sign, right? Big M is negative 19.6. So you have a minus and then a second minus, which of course gives you a plus. Now we're good to go. We plug in our numbers and we get something that this galaxy is 2.5, I guess this would be billion parsecs away. For reasons that will hopefully become clear in a moment, I will quote this in megaparsecs. Okay, 2.5 megaparsecs. Okay? But wait, there's more. We also have the redshift data for this supernova. So the same type 1a supernova has a redshift of 0.458. What's the distance to this supernova using, essentially, Hubble's law? Go ahead, take a minute, give me an answer. You got it? It's good. Now, the one thing I'll point out, we have to remember, what does c represent? Yeah, the speed of light. Okay. So I'm going to go ahead and put in the values that we have. We have everything we need. The one thing I will point out is that when I put in the speed of light, I'm going to express it not as 3 times 10 to the 8th meters per second, but rather I'm going to convert it into kilometers per second. And that's simply because I want some of the units from the speed of light to cancel some of the units from Hubble's constant. So let's go ahead. I'm going to cancel those units. And I've moved the compound fraction. And so the megaparsecs are now in the numerator. And now we just need to run our numbers. And no, you haven't done anything wrong. You will get a different answer. That's the whole point of doing this entire exercise. You get something that's about 1900 megaparsecs. Now, usually I tell you if you're within a factor of 10, then you're okay. This is one point where, okay, that's not going to work. These two methods should give us roughly the same answer. Okay. And this is one of the things that Perlmutter and his colleagues, the Nobel Prize winning paper, noticed. Okay. These two should be in agreement. Here's the out. Okay. We know we're fairly confident about the speed of light. Okay, C. We're really confident about type 1a supernova in terms of their absolute magnitude. So there's not very much leeway there. I mean, the question is, what could go wrong? Where's the problem at? So the one place that there could be an out that could explain why these two different distances don't match up better is in Hubble's constant. Assume that this redshift value is correct, and the distance measurement that we had on the last slide, let's assume that this is also correct. So write this down, this 2512 megaparsecs. Here's the new question for you. Based on this redshift value and that past distance, okay, what value for Hubble's constant would make both the redshift data and the supernova distance data agree? Go ahead, find that value. You got it? Okay, good. So now what am I asking you to do? We're going to apply the same equation, but over here in the distance, you're going to put the 2512 megaparsecs. And here Z stays the same. We're going to put that in. We're going to still put in the same value for the speed of light. The thing that we're swapping around now is trying to figure out what value for H naught would make my Hubble law approach give me the same value as my supernova approach. So I'm just going to rearrange. I'm going to put H naught to one side and I'll move the distance to the other. And so you notice I put in my redshift value. I'm still keeping the speed of light in kilometers per second, just like I did over here. And now I'm using the 2512 megaparsecs that I got from the previous question. You run all those numbers together, and you find out that rather than a value of 72 kilometers per second per megaparsec, you get something like 55 kilometers per second per megaparsec. In other words, to make the supernova data match with Hubble's law, we need a smaller value for the Hubble constant. Now keep in mind that a high redshift means that you are looking at a supernova that does not occur today, but that occurred in the distant past. Apparently, at the time of that supernova occurring, Hubble's constant was a lower value. Okay, so we have an idea, at least based on this one data point, Hubble's constant had to be smaller in the past in order to make the supernova data and Hubble's law approach agree. Okay, so this is for one example. The paper that I pulled this from does a couple dozen, 3 dozen, 4 dozen. So here's the data, and let me walk you through. I have used the data from the paper to calculate 2 distances. One distance using the fact that it's a supernova, just like we did for our first example problem. We know it's a type 1a supernova. We know the absolute magnitude. We can find the distance to that supernova. On the vertical axis, I have plotted the distance using Hubble's law and a value of 72 kilometers per second per megaparsec. Okay. Now notice, if the value of 72 for Hubble's constant is the correct value, then every single one of these dots, each dot represents an individual supernova. Okay. Each one of these dots should be on the red dashed line. What that would mean is that the distance calculated using Hubble's law agrees with the distance calculated using the supernova data. Okay. This dashed red line is at 45 degrees. So that means that if 72 is correct, then every single one of those dots should lie on the dashed line. Obviously, that is not the case. Right? You see that all of these dots lie below the red dashed line. In other words, calculating the distance using 72 for Hubble's constant underestimates how far away the supernova actually is. Right? This supernova is supposed to be at 4,000 megaparsecs. Hubble's law says it's only at 1,600 megaparsecs. So given that, we see that Hubble's law underestimates the distances to all these galaxies. What would the value need to be in order for Hubble's law to agree with the supernova data? That is what this cyan line represents. So we have the data, I fit it with the cyan line, and I find out that you'd need a Hubble constant of almost 40. And notice we're going further in the past. That's why it's lower than even what we had before. So apparently, the value that we use today for Hubble's constant, 72, what we've been using in this class, is higher than what Hubble's constant was way back when. And I'll say that this survey, the Z values are 0.7 to 0.83. That corresponds to 2.3 to 11 billion years ago. Pretty cool. So this is another question that we have to ask ourselves. What's causing the acceleration, right? I mean, we can get an idea about, okay, Big Bang. We don't know what caused the Big Bang, but if we accept the Big Bang, the fact that, okay, space started suddenly expanding. Okay. If we accept that, then we have an argument, we have a conceptualization about gravity. If space is expanding, gravitational forces from all the material inside the universe should start slowing down that expansion. And eventually, we should see that expansion slow down. This discovery by Perlmutter and this supernova data suggests not only is it not slowing down, it's actually speeding up. That's weird. right? We have a conceptualization of gravity. Gravity is attracting, it will slow things down, it'll pull it back together. We need something else that would explain why the universe is being accelerated. What's causing this? And that is the other topic for current research. We don't know what's causing that acceleration. We call it dark energy, right? It seems like when we don't have an idea about something, we just call it dark energy or dark something. Dark energy is another fix to our conceptualization of the universe. So that's all I have for you for today. Keep in mind, this lecture, what did we do? We said, well, what is the future of our universe, the end fate of our universe? And there we used high redshift supernova to determine the distance using supernova technique and Hubble's law. And in there, we found a discrepancy. We don't get the same distances. And that suggests to us that Hubble's constant used to be smaller in the past, and it's larger today. Well, the extrapolation of that would be that the universe itself is expanding at an increasing rate. Because of that, we now hunt for a mechanism that would explain why the universe is accelerating. And this is where we introduce the idea of dark energy. It is a fix to our model, a modification to our current understanding that helps us at least try to explain why the universe is accelerating. Now, we don't have a good idea what dark energy actually is, but we can at least say how much energy it must contribute in order to give us the observations that we have collected. You okay there? Sweet. Okay. Hey, thanks for your attention. We're getting up on the end of the end of the semester. I'm hoping that we'll break into some black hole stuff and end with a bang. Thanks for your attention. I'll see you next time.